potential difference, what do? You are asked to calculate the potential difference across the cell. So you just say your V equals IR. So your current is 1.25. So you just multiply it with your resistance, which is 6. So from there you'll be able to have 6 times 5, 33. 6 times this, 12 plus 3, 15. 1, 6 times this, 7. 6 plus what? 1, 7. 7.5 volts. Hope you saw it. It's very, very easy. Now let's go to number 3. Number 3 says calculate the terminal potential difference across a 20 ohm resistor connected to a battery of EMF this and the resistance. So you can see it's a very straightforward question. So let's go into another interesting topic. It talks about magnetic field. What's a magnetic field? Now, before we go into that, remember in our series we've been looking at field. Now we've given some different analysis of what field could be. So that shouldn't be a new thing to you. Now let's quickly go into some descriptive analysis as regards magnetic field. Number 1. Let's look at everybody uses magnetic forces, correct? Now, without them, there won't be what? There will be no electric motors. Now that you have the TV tubes, the loudspeakers, and the computer printers. Meaning that without the magnets itself, you understand? Magnetic forces or magnet itself, there won't be all these devices that we are actually using today, because we use a mechanism of magnetism were actually being used in the construction of those devices. E.g., we have your TV tubes, we have your loudspeakers, and we have your computer printers. Now, a magnetic field is a region. Are you getting it now? That's the actual definition. Magnetic field is a region around the magnet in which the influence of the magnet is being felt. It is to be a region now. Any particular region where the influence of magnet is felt, that region is called magnetic field. You understand? So that's the fundamental definition of what magnetic field are. Now, magnetic direction can be represented by using or by moving charge or a current that creates a magnetic field. Now, if you look at our diagram, you realize that we have something like this. Is a north pole and the south pole. This is a magnet itself. Now we have some flowing waves. It's actually invisible. Those flowing waves that explains the direction of the direction where an object is actually being attracted to. You understand? Those flowing waves are called magnetic flux. Magnetic flux. You understand? So those waves exist each time a magnet is super active. If you place your north pole with a north pole, something like this will occur. A north pole with a north pole face each other, they will repel. Why? Because they are like poles. But if you put an unlike pole, north and south, they will attract. So those are the little analysis when it comes to the way magnets interact. Now at this junction, we'll be looking at some terms. Now you have your F equals your QV, QVB sine phi. Now this is your fundamental formula when it comes to your magnetic field. Just put it upstairs that way. Now your B, let's start breaking it down. F is your magnetic force. It's called magnetic force. Now why your B? Your B is your magnetic field. Your force is measured in Newton. Your B is the magnetic field. Measured in Tesla. Are you seeing it? That's capital T. Your velocity, that's your V. V is the velocity. Now there is what we call phi. Your phi here is what we call angle of inclination. That's the phi. Now your Q are your your charges. So all these are terms that could be that could be obtained from the above formula written. So it is when you understand these terms properly that you'll be able to apply it. Now let's start with a very good one, angle of dip or inclination. Now this particular question normally surfaces when it comes to WAEC. You understand? Now a uniform copper bar, which is a non-magnetic, will stay horizontal if suspended at its middle. You understand? That is, if I have a rope now that is suspending, let me use a needle. You all know what they call needle. Now if I have my needle here placed there and I took a small thread to hold this needle, now logically if the point where I attach the needle is actually in the middle of what? That metallic object which is called needle. The needle will what? Be on a very straight horizontal section. It won't flip to either left or right. It will what? Be stable in terms of equilibrium. But listen to the statement. However, a magnetic needle will produce a different result when subjected to what? Center of gravity. What are we saying? If you have a needle, just a plain needle now, that's not being subjected to a magnetic field, it will what? Be straight horizontally. But when you have a needle that is being suspended in the region of a magnetic field, it will what? Towards to the other side or to this way. Now, if you check that statement, it says, however, a needle will produce a different result when suspended at the center of gravity. It is found that the needle will what? Will point downward at the angle to the what? Horizontal. This is called angle of dip. Now, meaning that if another needle now here is being suspended, but in the region of what? Magnetic field. Are you getting it now? So instead of it to go horizontal, it what? Go the other way around. So thereby forming an angle here. Now this angle that is actually being formed is what we call angle of dip. Now let's proceed. Now let's go to what we call theory of magnetism. So under theory of magnetism, we'll be looking at what we mean by diamagnetism, paramagnetism, and the other ones. For your level, we'll be focusing on just two. We have what the diamagnetism and the what paramagnetism. So although we still have ferromagnetism, but in this section we'll just be talking about the diamagnetism and the what paramagnetism. So let's start with theory of magnetism. It says if a magnet is broken in half, instead of separating north and south pole, we will obtain two magnets. You understand? No matter how a magnet is being broken down, each piece will be found to be what? Magnet with two poles. Very, very straightforward. If I have the magnet, a bigger one, we have the north and the south. If I break it down, I will have north-south straight up. If I break this one too down, something like this, I'll have north-south. If I break this down, I'll have north-south. So irrespective of the magnitude of what I'm actually breaking down, irrespective of the size, there will always be a north and south pole. That's a major theory under magnetism. No matter how you crush your poles of magnet, you will never separate the north and south pole. They will always be together. There will always be two sections of pole. That's the number one theory of magnetism. Now let's go to our diamagnetism. Now in many materials, there are as many electrons spinning or orbiting in one direction as the opposite direction, so that they are what? Effort neutralizes one another. What are we saying? Opposite direction. No, those electrons are in opposite direction. Now at the end of the day, we have what? Their effort neutralizing each other. But when we apply magnetic field, the electron orbits are slightly disturbed by the induced electromagnetism, which reduces the field strength inside the material, giving rise to the little magnetic effect called diamagnetism. So it means that those electrons that are actually facing each other, when you induce electromagnetism into this particular field, it affects the direction or movement of those electrons. If you look at that statement, it says, but with the applied magnetic field, the electron orbits are slightly disturbed. You understand? Now, by the induced electromagnetism, which reduces the field strength, you understand? Inside the material, giving rise to the little magnetic effect called diamagnetism. Electromagnetic field. What is actually electromagnetic field. Now in this section, we'll be dealing with a lot. Yeah, under that, let's look at the concept. When a charged particles with a charged Q move through a region of space with both electric and magnetic field E and B vectors respectively are present, forces are being experienced in both fields. Are you getting it now? So when your charged particles is actually moving from A to point B, you understand? Now it's now moving in a place where, or in a platform where that has both fields together, that is magnetic field and what? Electrical field. You understand? So your magnetic field is denoted by B, while your what? Electric field is what? Denoted by what? E. When that charged particle Q move from this point to this point, and there is an existence of the magnetic field and electric field in this platform, so definitely Q will experience the properties of a magnetic field and what? Electric field. Hope I get this down. Now from our formula, it is being noted that a force is being induced. Total force will now be the force of the what? Magnetic field plus what? Force of the electrical field. So those are the two what? Forces that exist, you understand, in what? Your electromagnetic field, because electromagnetic means two fields in one. You understand? A platform where two fields exist in one. Now this is known as Lorentz force of a current carrying conductor placed in the magnetic field. Now the force F on the wire can be shown to be what? Proportional to 1, the current, and 2, the what? Length of the wire. What does that mean? Length of wire directly proportional to length of wire and directly proportional to what? Current of wire. This expression means that the higher your force, the higher your what? The length of wire. The higher the length of wire, the higher the force that we experience. Now, the higher the current that flows in your wire, the higher the force that we experience. Now, the third point is that the sign of the angle that the what? Conductor makes with the field. Okay, I'm getting it now. So from there, now we'll be able to obtain another formula which is combining both your electric field and your magnetic field. So from here you have your FB